Ladies and gentlemen, now, we will start the last lecture of the control phase. During the lecture, the following topics will be covered: control chart using Sigma XL, control chart using Minitab, control charts for discrete data, standardization, reaction plan process management diagram. To develop control chart for any data using Sigma XL, click Sigma XL, then Control Charts. Now, you can click any type of control charts: X-bar in R, X-bar in S, IMR, and attribute charts, P, NP, C, and U. Or click Sigma XL, then Control Charts. Then click Control Chart Selection tool. Select the data type continuous or discrete. Then select subgroup size for continuous data. However, for discrete data, please select first detective or defect, then select the subgroup data, and let Sigma XL choose the type of control chart that is suitable for your data. For example, for X-bar and range chart, select the numeric data variable, then select X-axis label. Check Calculate Limits, and check Tests for Special Causes, and Sigma Zone Lines. Then click OK. The two charts will be plotted, and the special cause of variation points will be highlighted in red. The Test for Special Causes report gives us more detail about the recent instability. Both the X-bar chart and range chart, in addition to the Tests for Special Causes report, clearly show that this process is now out of control with an unstable mean. The process must be stopped, and the out-of-control action plan must be followed to determine and fix the root cause. The use of Tests for Special Causes gave us an early warning of this problem at observation number 1, 12, 13, 14, 15, and 16. Here are the control charts after taking an action plan and solving the problem. The Test for Special Causes report shows that there is no special causes of variations and no failing test points. To develop the control charts using Minitab, click Stat, then Control Charts. Then choose either variable charts for subgroups, or variable charts for individuals, or attribute charts. Then finally, click the selected chart type according to your sample type and size. Select the subgroups, and click OK. The two charts will be generated, with the failing test with special cause of variation marked in red. Now, we will start to construct the attribute charts, and we will begin with the P chart. A production manager at a tire manufacturing plant has inspected the number of defective tires in 20 random samples, with 20 observations each. Following are the number of defective tires found in each sample. Step 1. The classification data, with the proportional defective, within a variable sample size are shown in the table. The P chart will be used. Step 2. Calculate the center line, as shown. Step 3. Calculate upper and lower limits. The UCL and LCL values need to be recalculated for every observation, as shown in the two equations. We will replace all the minus numbers in the LCL with zeros. Step 4. Select Scale and Plot, and check for special cause of variation. A textile manufacture facility makes fabric pieces with specific dimensions for sportswears. Occasionally, a quality test yields inconclusive results, and items must be repeated. Using the following sample data, and n equal to 200, determine the upper and lower control limits for the fraction of retests. Is the process in control? If not, eliminate any values that are outside the limits and compute the revised limits. Please pause the lecture and solve the exercise. We have number of defective parts and subgroup size is fixed, so we will use NP chart. Using sigma XL, enter the numeric data variable, subgroup size, and C-axis label, then click OK. The NP chart shows that the process is out of control, and there is a special cause of variation. We have to eliminate such point by reducing the number of defectives in the process. Repeating the chart again to check the operation after eliminating the special cause of variation. Now, we will construct the C chart. The number of daily defects items in a process are shown in table below. Use the corresponding chart type to formulate the control chart for the process. Step 1. Count the actual number of defects. For example, we can count the number of complaints from customers in a month, the number of defective parts per day, or the number of failures per operation. However, we cannot compute the proportion of complaints or defects. We will use the C chart, as C chart is used when we can compute only the number of defects, but cannot compute the proportion that is defective. Step 2. Calculate the center line, the number of defects divided by the number of units. Step 3. Calculate upper and lower limits, according to the equation. LCL is negative and rounded to 0. Step 4. Select Scale and Plot, and check for special cause of variation. The U-chart tracks the number of defects, not the number of defective parts, as done in the P-chart and NP chart. For any given part, you can have 0 to n defects. Defects are things like scratches, dents, chips, paint flaws, etc. Think of the last car you bought. Also, a defect does not indicate any magnitude of defect, such as might be measured in one of the variable control charts, only that it is or is not a defect. If you were monitoring a process using both P charts and U charts, the P chart may show that 55 parts were defective, while the U chart shows that 175 defects were present, since a single part can have one or more defects. The U chart differs from the C chart in that the inspection unit size, subgroup sample size, in a C chart is fixed, while in a U chart it can vary from subgroup to subgroup. Since the plot value is a fraction, or percent of the sample subgroup size, the size of the sample group can vary without rendering chart useless. In this case, the control chart high and low limits vary from sample interval to sample interval, depending on the number of samples in the associated sample subgroup. A low number of samples in the sample subgroup make the band between high and low limits wider than if a higher number of samples are available. Please perform activity and send your outputs by email for assessment. At each stage, the center line and control limits on the chart should be recalculated. Now it's easy to see that this process was kept in control at every stage of improvement, and you also get much more accurate idea of how the center line went down at each stage of the improvement. You can also see that the variation of the process, the area between the upper and lower control limits, decreased over time. Example shows how the improvement in the process will affect the center line and control limits. Control charts are used to control place air voids in road pavement. Contractors are most concerned with specification limits. Control charts are set up to compare production material to specification limits. However, often in the case of in-place air voids, only a lower limit is specified. Note that there are no specified limits for the sample range, so no limits are shown on the R chart. Using the control chart shown in previous figure, it looks as if the process is well below the specification, and all is well. After a certain number of samples, usually about 20 to 25, upper and lower control limits can be established to further monitor the process. Keep in mind, these limits are not specification limits and are only based on averages and ranges of actual measurements. Upper and lower control limits should be based on average values, average sample ranges, and sample size. In our case, each data point represents the average of 5 samples in the X chart and the range of these 5 samples in the R chart. After 40 measurements, 40 lots, the control charts changed. In the X chart, the process seems to have shifted down to some new lower average. In general, this is a good shift because the lower air voids are generally better. However, this shift to the lower air void should also trigger a check of asphalt content to ensure that it is not caused by a high out of specification asphalt content. Note also that the range control chart shows the sample ranges have increased slightly. Assuming lower air voids are desirable, it would be practical to adjust the control limits at this point to reflect the changed process. New control limits are set, which are based on measurements 20 to 40, lots 20 through 40. Note that the average in-place air voids have increased from measurement 40, lot 40, to the end, which should trigger an investigation to determine the cause. Measurement range seems to have stayed relatively consistent from measurement 20, lot 20, to the end. Although in place the air voids were within specification for the entire project, the control chart located 2 process shifts, at lot 20 and lot 50, that may have otherwise gone undetected. Please download the educational video from the resources Control Chart Excel.mp4, Control Chart Sigma Excel.mp4, Control Chart Minitab.mp4. What is the standardization? When working to improve a process, it is not enough to implement a solution and stop. Without a plan to maintain the gains, at the first sign of trouble, systems will revert to what has been comfortable in the past. That usually means a return to some past operating procedure. To prevent this, there must be a linkage of the improvement to the management system. This involves monitoring important metrics, documenting methods and procedures, and providing a strategy for dealing with problems in the future. Standardization of the should-be process steps is required to ensure all responsible for execution have the same understanding to do it now and in the future. Standardizing the should-be process helps answer queries like, what are the steps in the process? Who does these steps in the process, and when? Where more detailed work instructions can be found. Standardization has three components. 1. Elimination of waste. 2. Workplace simplification, 5S philosophy. 3. Work process analysis. A typical work process analysis goes through 3 stages. 1. Process documentation. 2. Process measurement. 3. Process analysis. Documentation is an underlying principle in standardization. Making sure documentation is up to date and utilized encourages the ongoing use of standardized methods. In addition, documentation provides the information necessary to anticipate problems and to see where potential improvements can be made. Process analysis in control phase includes process sigma level, process capability, goals of the reaction plan. It is clear what is to be done when a CTQ is violated. Respond quickly and effectively to changes in a CTQ. Immediate reaction and launching of measures are possible. Control over what is happening. Steps to make the reaction plan. 1. Examine the improved process in detail for those places where a problem may occur, using an FMEA. 2. Drive the necessary measures for each point and nominate a responsible person. 3. Draw up a process management diagram. 4. Monitor the process. The reaction plan comes into force when a CTQ is violated or changes. Example of process management diagram. Now, we will perform checklist for the control phase. In case of any unmarked point from your point of view, please replay the 3 lectures of control phase, check the course materials, watch the instructional videos, check the templates, and perform the activities. We will perform the checklist for the following: documentation and standardization. The new improved processes are documented in a complete and detailed way, in line with company guidelines. Detailed and understandable procedural instructions are drawn up. Monitoring and control charts. Key performance indicators are selected and operationally defined. A data collection plan is drawn up, and the capture of data is secured. The approaches for depicting and evaluating data are defined. The process owners understand this depiction and evaluation. The process owners have agreed to undertake the monitoring. Reaction plan. A reaction plan was developed. The process owners understand the reaction plan. The process owners have agreed to use the reaction plan. Implementation. Implementation is undertaken systematically until successful completion. It is time to develop your project. Design control charts for the collected data after improved phase, and interpret the control charts to check the process improvement. Make the standardization documents, reaction plan, and process management diagram for your project. Thank you, and see you in the next lecture, which will handle the Mini-Tab Assistant tool.